Hey Physics 1 students, welcome to this day of physics class, and you're going to get to do an experiment at home today. You're going to measure the speed of light. Well, technically the speed of microwaves, but they travel the same speed as light. To do this, you're going to need a few things. You're going to need some chocolate chips. Maybe not a full bag, but certainly at least a half of a bag of chocolate chips. You're going to need a piece of cardboard. Doesn't need to be quite this big. If it's the same size as a sheet of paper, you'll be fine. You're going to need a ruler, and that ruler is going to need to measure in centimeters, all right? So you need a ruler. You're going to need a spoon of some sort, because when you're all done, you're going to eat the chocolate chips, of course, but you also need it to find the gooey parts. We'll get to that in just a minute. And finally, you're also, if you look up here, you're going to need a microwave, all right? And so that's the other thing we're going to be using today. All right, so how are we going to find the speed of light? Well, we're going to begin with the wave equation, which says that velocity equals frequency times wavelength. And for all electromagnetic waves, velocity is the speed of light, which we use the symbol c. You learned that on Thursday. So the speed of light is the frequency times the wavelength. So quite simply, if we can discover the frequency and the wavelength of a wave, then we will know the speed of light. Now today we're not going to use light per se. We're going to use another part of the electromagnetic spectrum. We're going to use what are known as microwaves. And so yes, you're going to need to use your microwave to do this experiment. All right, as we just learned, one of the things you're going to need is the frequency of the waves. So what are the frequency of microwaves bouncing around in your microwave? Well, if you look right here in mine, you're going to find that there's a sticker, and you'll have a sticker in yours too. And if you zoom in right there, it says output frequency, and I believe it says something like 2,450 megahertz for this microwave. All right, guys, so we found the frequency of our microwave as it was stamped on the microwave, and you'll have to look for yours, but ours was 2,450 megahertz. Mega is 10 to the 6th, so that's 2,450 times 10 to the 6th hertz. So a quick conversion of that shows that frequency is 2.45 times 10 to the 9th hertz. That's the frequency of the microwaves bouncing back and forth inside of our microwave. All right, so now we come back to our wave equation. Remember, we said the speed of light was the frequency of the waves times the wavelength. And we now know the speed of light is our frequency, 2.45 times 10 to the 9th hertz, times our wavelength. But what is the wavelength? Well, that's what we're going to do next. We're going to find the wavelength of the microwaves in our microwave, and that's what we're going to use our chocolate chips for. All right, so here's what we're going to do. We're going to take these chocolate chips, and we're going to spread them out all over our piece of cardboard. All right? You want to spread them out so you have a nice collection of them and you don't have any gaps where you don't have any chocolate chips. All right, so you want a pretty good collection of chocolate chips. You'll notice that I'm getting quite a few down here. All right, and then when you get them on the board, you're going to spread them out all nice and even like this. All right, just kind of nice and even like this. Okay, now here's the idea. The microwaves that heat your food are standing waves, just like standing waves on a string or in a resonant tube. These are represented by the blue lines on this paper. Now you know that a full wave is from one node, skip a node to the next. That's a full wave. And so what happens in a microwave is it heats your food, but it doesn't heat it evenly throughout. You know this, because you put food in and some areas are cold when you take it out of the microwave and some areas are hot. And so the areas that are hot get hot the quickest. That's where you've got nodes in the waves. And so that's going to be the most intensity of the energy, all right? And so what we're looking for is to see where the chocolate chips are going to melt the most. And then what we're going to do is know from the distance from one area of melting to the other is going to be about a half a wavelength. It'll be a half a wave because node to node is a half a wavelength. All right. All right. Now, one problem with this is your microwave has a turntable. And that's purposely put in there so that when you heat up food, it heats up evenly. So one of the things we got to do before we put these chocolate chips in the microwave is we've got to go ahead and take out our turntable. So we're going to take that out, and we're going to take this out. And now we're going to go ahead and put our chocolate chips in the microwave. So I'm going to go ahead and put them in right here. And by the way, our light went out on the microwave and I haven't gotten to do one. So there it is right there, and now we can close the door. Lastly, we're going to go ahead and run the microwave for about 25 seconds. Not much more, 25 to 30 seconds. So time cook, 25, and we're going to go ahead and hit start. All right, so let's go ahead and let this cook for about 25 seconds. I'm going to stay with you while we do this. Now, while that's cooking, I'm going to go ahead and get my spoon ready because I got to find the gooey parts of the chocolate chips. So here we go in just a minute. All right, okay. Let's see where we are here. We just got a few seconds. All right, and so we're going to very carefully take the chocolate chips out. We're going to bring them over to the table. And now we're looking for gooey areas. There's a gooey area. And you can kind of push down with the spoon and find the gooey areas. Hoping I get another one here. Yes, there's another gooey area. So those are pretty solid. All right, and we have gooey area, and gooey area. So we've got 3 nodes. I'm going to mark them. We've got one here, we've got one here, and we've got one here. So that total distance will be, that's half a wave, that'll be a full wave. So we're going to go ahead and my gooey parts are about 13 centimeters apart. So from one gooey area to the next is about, maybe 6.5, and then another 6.5. So 13 from here to here, which is one full wave. From node to node to node is one full wave. All right, as we showed, remember, if you look here, from node to node to node is one full wave, and we've got about 13 centimeters. All right, so back to our math. Remember, this was our frequency of our microwave, and we just measured the wavelength to be about 13 centimeters, which is 0.13 meters. And if we multiply those two together, we get a speed of sound of about, let me do the math here, 2.45 times 10 to the 9th times 0.13, and I get 3.19 times 10 to the 8th meters per second. So that's the speed of light, or the speed of the microwaves, which is also the speed of all E&M waves and the speed of light. Now, how close is that to the accepted value? Well, the accepted value is 3.0 times 10 to the 8th, so we're pretty close. One of the things you're going to do is find the percentage error. All right, so there we go. We found the speed of light with chocolate chips, and it's a wonderful little experiment to do because it's really tasty too. Now, a couple things to remember. There's Mark. That's our cat, our new kitty. But here's the deal. If you don't have the ability to do this, then you can use the data I have today. However, I'd really like you to do it on your own. So get the chocolate chips, get the chocolate bar. Chocolate bar will work just as well. One of the big ones, you get at the store, they'll get gooey. And again, every half wavelength intervals. If you don't have a microwave, then boy, I feel sorry for you. But this should work. So we'll go ahead and give this a try. Submit your findings and upload them tonight. And thanks for doing this tasty lab.